In this video, we're going to continue working through SAT practice tests. As a reminder, this video is part of a playlist where we're working through each of the practice tests in the official SAT study guide. So the intention behind these videos is to give detailed explanations on how to consider these kinds of problems from different perspectives. So if you're interested in this content, head over to the channel and watch the other videos in the playlist. Okay, so here we're working through problems 6 through 10 of section 4 of the first practice test. This is the second math section where calculators are allowed. Alright, so let's get started. Problem 6. In problem 6, we're told that a hospital stores one type of medicine in 2 decagram containers. Based on the information given in the box above, how many 1 milligram doses are there in one 2 decagram container? Okay, so the way so what we're asked to do is go 2 decagrams, and we want to figure out how many milligrams that corresponds to. And this is a very direct unit conversion problem. And so this problem is an excellent opportunity to go over the anatomy of unit conversion, and try to avoid some of the pitfalls that are very common when we're doing this type of analysis. So we're going to start by looking at the first relationship we're given, right? 1 decagram is equal to 10 grams. And now I'm going to do something that might seem a bit puzzling at first, and I promise you we won't always do this, but since this is our first in-depth look at unit conversion, I want to be a little bit more explicit, right? So I'm going to divide both sides of this equation by 10 grams. So we'll have 1 decagram over 10 grams is equal to 1, right? And I'll also do the same in the other direction. So we'll divide both sides of this equation by 1 decagram. So we get 10 grams over 1 decagram is equal to 1. Okay, and then we'll repeat this for the second relationship we're given, right? So 1,000 milligrams is equal to 1 gram. So that is equivalent to 1,000 milligrams over 1 gram is equal to 1. And the other way is also true. Okay, and what we'll call each of these fractions, we'll call them conversion factors. Okay, so it might seem a bit strange that we're doing this at first, but bear with me. This will become clearer as we work through the problem. Right. So in this problem, we're told that we have 2 decagram container. Right. So let's just consider one of these 2 decagram containers. So one such container will have 2 decagrams of medicine. Right. And I'm going to write it as a fraction. I'm just writing it as 2 decagrams over 1. The reason I write it as a fraction is because, as you'll see as we work through this problem, we're multiplying fractions, and so I think it's more consistent, at least in terms of appearance, to write everything as a fraction, right? And then I'm going to multiply this by 1, and multiply this by 1 again. And you might be thinking again, hey, this is kind of a strange thing to do, right? Why are you multiplying something by 1 twice? Well, the first argument that I'm going to make is this is still 2 decagrams, right? We haven't changed anything. When we multiply anything, any numerical quantity by 1, we get that exact same numerical quantity back. That's axiomatic, right? And now the second thing that I'll point out is, well, we multiply by 1, and we have 4 different ways of writing 1, right? So theoretically, I could substitute this one for one of these, and this one for another one of these, right? And so this is basically the whole game with unit conversion. We're multiplying a quantity by 1, and then by 1, and potentially by 1 again, and again, and again, right? Until we get the quantity of interest on the other side of all this multiplication. And the trick becomes what version of 1 should we multiply by? And the way to kind of answer that question is to think, okay, in the denominator of one of these conversions, look at the quantity that you want to go from, or sorry, the unit that you want to go from. And then in the numerator, you should have the unit that you want to go to, right? So in this problem, we have decagrams in terms of grams and milligrams in terms of grams. So what we have to do is first go from decagrams to grams, right? So we'll go to grams here, and then we want to go from grams to milligrams, right? So this first conversion factor should have a decagram in the denominator and a gram in the numerator. So we're picking this guy. And then our second conversion factor should have a grams in the denominator and a milligram in the numerator. So we're looking at this guy. Right? Okay, so let's go ahead and actually do that multiplication and see what we get. So 2 decagrams over 1 times, we're looking at the orange box now, so 10 grams over 1 decagram. And now we're looking at the yellow box, so that's going to be 1,000 milligrams over 1 gram. And we know that this is still equal to 2 decagrams, right? So I'm literally just making some substitutions in this first equation. And now we start to see the cancellation that we talked about. Decagrams are going to cancel, grams will cancel, and we'll be left with units of milligrams. So we get 20,000 milligrams is equal to 2 decagrams, right? And now our problem says how many 1 milligram doses are there in one 2 decagram container. So I mean, if we want to be very pedantic here, right, we can say, well, 20,000 milligrams, right? And then so that's how much medicine we have, right? And we pack it into 1 milligram doses. So in 1 milligram dose, there's 1 milligram of medicine, right? So that means that we have 20,000 milligram doses, right? Because these milligrams cancel. So I mean, this last step is really just, it's optional, right? It's you know, how you know, precise or pedantic do you really want to be? You know, I feel like precise is maybe not the right flavor of describing what we're doing here. But anyways, as soon as we get to this step right here, right, we've solved our problem. And so what we can conclude is that the correct answer choice is D. Okay, so let's just recap here what we did here for a second, right? So you identify your conversion factors, right? And then what you want to do is pick the right conversion factor depending on the quantity that you want to go from to the quantity that you want to go to, right? And then you just and then you have to remind yourself that what you're doing when you're multiplying by any of these conversion factors is multiplying by 1. And that's totally legal. You're always allowed to do that, right? Okay, so that's sort of the anatomy of a unit conversion problem. Okay, so let's now consider problem 7. So I'm going to jump here for a second. Problem 7. Okay, I'm going to move this a little bit this way. Okay. So in problem 7, we're given this graph, which represents the number of solar panel installations in 5 cities, in cities A, B, C, D, E, and we're told that the total number of installations is 27,500. So what is an appropriate label for the vertical axis of this graph? So let's take a look at the number. So let's look at the answer choices. So A, we have a number of installations in tens, right? So really the only thing that changes between the answer choices is the denomination, right? So where we have in tens, hundreds, thousands, and tens of thousands. So our problem really is to identify what each of these little unit bars, right, represents, how many panels each of these bars represents. So let's actually, this is an opportunity now to leverage our newfound tools in unit conversion, right? So we want to find, so let's write down our data, right? So we have this graph. So I'll just draw it very roughly, just eyeballing this, right? So this is A, B, C, D, E, right? And we have 9 bars here, 5 bars here, 6 bars here, 4 bars here, 3.5 bars here, right? And we're asked to find, this vertical axis label. Okay, so let's go ahead and give ourselves a variable to work with, right? Let's let X represent the number of panels per unit bar. Okay, so explicitly what that means is how many panels is actually represented by one of these bars, right? This is what we mean by X. Okay, so what we can do is add up the number of unit bars we have. So that's going to be 9 plus 5 is 14, plus 6 is 20, plus 4 is 24, plus 3.5 is 27.5. So we have 27.5 unit bars, right? So if we were to multiply 27.5 by X, right? So let's do that. 27.5 unit bars times X panels per bar, right? Then we would get 27.5x panels, right? The unit bars are going to cancel here. And what we're told in the problem statement is that we have 27,500 total installations, right? So 27.5x panels is actually equal to 27,500 panels, right? So that means that X is equal to 1,000 panels per bar. Right? We're simply dividing both sides of this equation by 27.5. So what that tells us is that each of these bars represents 1,000 panels. So if you look at our answer choices, that corresponds to answer choice C. So the appropriate vertical label for this type of graph is the number of installations in thousands. Okay, so this is kind of a fun way to see how unit analysis is helpful to us. It's by no means necessary. Like again, you can think about this problem as just adding up the number of bars and then you can conclude that each of these bars must be 1,000 panels. But I think that this is a good way to see how unit analysis is useful in many different types of problems, even where you might not immediately think of using it. Okay, so now let's look at problem number 8. In problem number 8, we're asked to find the value of n such that the absolute value of n minus 1 plus 1 is equal to 0. Right? So, maybe I should say that n equals question mark. Right? So this is what we're trying to find. So let's go ahead and try to solve this algebraically, and then I'll show you a graphical way to think about this problem using your graphing calculator. So we're told absolute value of n minus 1 plus 1 equals 0. So we can subtract 1 from both sides. So we're told absolute value of n minus 1 equals -1. Now this should actually start ringing some alarm bells for you. The reason is that we have an absolute value of something being equal to a negative number, right? And if you remember, absolute values should always be positive, right? Absolute values represent the distance, on the number line of a given number from 0, right? So when we have 0, right, and we have x, and let's say we have negative x, the absolute value of both of these numbers in this case should be x, because you're x units away from 0. It's literally a distance, right? Or sometimes you'll hear people use the term norm. Okay. But, so this should start ringing some bells for you, but let's go ahead and keep working here for a second, right? So normally when you have something like an absolute value of x is equal to y, right, the way you solve that is you look at two different cases, right? So you say x is equal to y or x is equal to negative y, right? So let's go ahead and apply the same approach here, right? So we have, if we look at case 1, we have n minus 1 is equal to negative 1, right? And then we'll have n minus 1 is equal to 1. So if we go ahead and use this, right, we get n is equal to 0. And in this case, we have n is equal to 2. Okay, so now you might be tempted to say, okay, well, n is either 0 or 2, and that's it. But with absolute value problems, you always have to go back and check your original expression, because you may have inadvertently done something a little illegal, and it may not be obvious to you where the problem came, right? So just go back and plug your candidate answer choices back into your expression. So let's say if you plug in n equals 0, right? So we have 0 minus 1, right, plus 1 equals 0. So the absolute value of 0 minus 1 is negative 1. The absolute value of negative 1 is 1 plus 1. So this should be a question mark. So is that 0? So we're 2. So 2 is definitely not 0. So 1. So this answer choice, n equals 0, is not valid. Okay, so now let's go back and do the same thing with 2. Right, so the absolute value of 2 minus 1 plus 1 equals 0, question mark. So this is 1, right? So this should give you 1 plus 1. And again, we get the same issue, right? So n equals 2 is not a valid answer. So in fact here, there's no valid answer, right? Because absolute value can never be negative, right? That's what we can conclude just from this first statement. So now I think that another way to think about this problem is graphical. And this is actually a good opportunity to use to get comfortable with the graphing calculator. So I'm pulling this graphing calculator onto the screen. Right, and what we'll do is we'll actually graph the function absolute value of x minus 1 plus 1, okay, and we'll see if it's ever equal to 0. Okay, so you'll go to y equals, right, and you can start typing in. So you'll go to math, and then you'll go to num. Well, I guess you have to go from here, num, abs, and then we'll look at x minus 1, right, plus 1, and then we can look at the graph. So what you see is a graph like this, right? So this is what your graph looks like, and when we're looking for, and when the problem asks us to find where it's equal to 0, what you would think about is essentially if you were to draw another line, right, where y equals 0, so if you just look at this x-axis, right, you want to see where it intersects the x-axis, and you see that there's no value of x where this is true. So this is a graphical way to kind of think about what we're asked to find here. And we'll revisit this graphical, using our graphing calculators to solve equations very shortly, but I just wanted to prime you to that right here. Okay, so good. Let's move on now to problem number 9. So let's move here. And we're going to move it a little bit onto, I'll just move it so you can really see the problem. Okay. So we're looking at problem 9. So questions 9 and 10 refer to the following information, where A equals 1052 plus 1.08t. So in this formula, A, so I'll just write it as data for problem number 9, but we'll reuse it for problem 10, right? So we're told A is equal to 1052 plus 1.08t, where A is the speed of a sound wave. So speed of a sound wave. And this is in feet per second. So you notice how the College Board gives you units, right? So this kind of corroborates that it's good practice, right? And then T is air temperature. And this is in degrees Fahrenheit. Okay, and in problem 9, we're asked to find the air temperature in terms of the speed of a sound wave, right? So notice the information we're given is speed of a sound wave in terms of air temperature. So we're told A in terms of T, and now we want to find the air temperature in terms of the speed of a sound wave. So we'll find T in terms of A, right? So what we need to do is take our initial equation and solve it for T. So let's go ahead and do that, right? The first thing we should do is subtract 1052 from both sides. So we're left with 1.08t. And then we can conclude that T is equal to A minus 1052 over 1.08. So that corresponds to answer choice A in this case. Okay, so now let's move on to problem number 10. So in problem 10, we're asked, at which of the following air temperatures will the speed of a sound wave be closest to 1,000 feet per second, right? So here, remember, we have the relation. So we're basically asked for what value of t, right? For what value of t is A going to be 1,000, right? So let's write that. So A equals 1,000, right? So T is question mark. So if we wanted to do this purely algebraically, right, we would take 1,000 and substitute it into our expression, right? So 1,000 equals 1052, right, plus 1.08t. So we would get negative 52 equals 1.08t. So t would be equal to negative 52 over 1.08. Right, so that is equal to approximately, and now let's bring our calculator back onto the screen. Okay, so we'll go, let's bring it all the way on. Negative, we should use this negative 52 divided by 1.08. So we get negative 48.15. Right. So our answer in this case will be negative 48.2, which corresponds to answer choice B. But as I promised, I want to show you how you can really use your calculator to your advantage, because this is a skill that'll go beyond, just the SAT. So we'll look at two different things, right? So the first will be using the solving function, or the solver of calculator, and then the second will be the graphical approach. Both of these use the same underlying algorithms within your calculator, but I think, depending on what style you prefer, you can opt for one or the other, right? So let's look at the solver first. So the way to use a solver is to go to math, right? And then you're going to just scroll up and you see there's an option for solver. So we're going to hit enter. And how the solver works is you're given two equations and you're looking for the value of your unknown, right? So in our first equation, that's going to be 1052 plus 1.08. Instead of x, I'll just use t just because that's what the solver sort of prefers, right? And then our second equation is going to be 1000, right? So we're told, so remember, this is a, right? So 1052 plus 1.08x, or t, right, is your speed of sound. And then we're looking for where that speed of sound is equal to 1000, right? So this is literally, it's literally writing out this equation. So 1000 equals 1052 plus 1.08 t. And so you might be thinking, well, why would I use a solver for something, that I can do by hand? And that's a valid question, but sometimes you might be looking at equations that are not solvable by hand. So then you'll go down, right? And you see that what we're told here is that equation written out, and you have to supply an initial guess for x, right? So oftentimes, especially with these kinds of linear equations, the initial guess isn't so important. So I'm just going to leave it as it is. Okay, and then you have to give bounds. So this is basically the values of x which you would want to consider. So these are massive numbers. So you're essentially looking for all values of x. And then you're going to go alpha, enter, and when you click that, you're saying solve. So you say enter, and you see that it gives you x is equal to negative 48.15, which is exactly what we found, right? I should point it out here, negative 48.15. Okay, so that's if you want to use a solver. What if you wanted to think about this problem graphically, right? So the way that I would do that is I would say, okay, let me clear this, and I'll graph out each of our equations. So we'll say 1.08 x, right? So that's our first equation for y, and now our second equation will be 1000, right? And what you want to do is first of all, let's graph it to see what this looks like. You see, you won't actually see anything on your screen, so you can click zoom as soon as it's ready. And you can say zoom fit. So you can actually see both of your equations on the same graph. Okay. And you see that I'm going to zoom out for a second, so I'm going to zoom out. Zoom out. And I think I'll zoom out one more time as soon as it's done graphing. So let me zoom out one more time. Okay, good. So at this point, what I'm going to do is go to second calc, and I want to find the intersection of these two graphs, right? So the reason that I want to do that, right, is because really what you're looking for is when we're looking at these a solution to this equation, right? We want to say, where is it that 1052 plus 1.08x is equal to 1000, right? And so we're looking for the value of x where these two equations are both true. And that is, of course, the intersection, right? So this is, if you think about a system of equations, this is the intersection of your system, of your two equations, right? So now you have to say, well, what's my first curve? So that's this guy. What's my second curve? Well, that's the red line. And then you have to supply a guess again. So you can kind of eyeball where you're close, and then you just want to get reasonably close so that you can solve quickly. But again, with these sets of linear equations, it's not a big deal. And then you hit enter, and it tells you that the intersection is negative 48.15, right? So again, you get the same result. You get negative 48.15. So either way that you'll get the same answer, but you can start trying to think about how to use your calculators when you have questions that are a little bit more complicated. And I guess oftentimes when you want to verify your intuition by graphing out a function, you use your calculator, especially where you're able to, right? Okay, so that's all I wanted to say for these 5 questions. We'll pick up the next 5 in our next video. Thank you very much. See you in the next video.